Hello, everybody. Thank you for joining today. Today is a special webinar topic. Um, yeah. Before starting, I would like to know where are you based because we are a lot of people today here. Um, I'm based in San Francisco, and then we are going to be joining here our CTO and our CEO in San Francisco. So could you use the chat to let me know where are you based today? I'm curious about it. Oh, Los Angeles. I'm going to include Jonas and Tema today because I think this is good
Hi, everyone.
to know.
Hello.
From Germany, Dallas. Wow. Seattle, Israel, California,
Austria.
Canada. Good. New
Paderborn.
Jersey,
Paderborn.
Finland, New
Paderborn.
York. Oh, a lot of people in our time zone today, right?
Maybe the reach of the
Iran, USA, Paris. Okay, so thank you everybody for joining today and to be here on live. Today we have two our main members in the team in San Francisco office. So yeah, up to you. You can start when you want. Tema and Jonas, thank you for connecting today.
Wow. Thank you very much. Thank you very much, Ellie, for the introduction. I'm here hosting today this webinar in our office in San Francisco. And I have with me this week Jonas. So, Jonas, how do you like San Francisco? Are you still having some jet lag?
Well, I'm here since like for 3, 4 days, so jet lag is almost phasing out, so no problems. Yeah, I love it here. I love San Francisco. You see when you walk around the city that there is a lot of things happening in the tech industry. And just a little story, I was on Sunday working in a coffee shop on our future product here at Frenetic, and then a guy approached me and we had a very good discussion about the tools I'm using and how to use them properly and so forth. So I think that wouldn't happen in another city, that you have these very spontaneous exchanges about the things you're working on at the moment. So I really enjoy the city.
I really can confirm that that's happening. So the only sport I practice is tennis, and every time I play a tennis match, there are 10-15 minutes about talking about, hey, are you investor or entrepreneur or working in a startup? So that's actually the typical conversation, and I have met incredible people just going out of fun. Okay. Well, the other thing super interesting is that we have here in San Francisco now a lot of people of our team and working together in new products. So I think that in the next months, you will see very interesting stuff. How do you feel about working now in the same place after a lot of remote hybrid? Now we are a lot of days together. Do you feel like this is really making a difference?
Yeah, definitely, yes. I mean, we are in Madrid, Zurich, and San Francisco based, and there are 9 hours time shift between San Francisco and Europe. So it's quite challenging sometimes to find an overlap and have useful meetings. Often people are tired in Europe and still fresh in San Francisco. So now we're all together here, and I think it's make things easier, and yeah, it's a good atmosphere also.
Okay, so as always, we try to keep the webinar in less than half an hour, or let's say half an hour, around half an hour. So we are going to directly jump to the topic. So I have prepared some slides. It's gonna be just 3, 4 slides, and then after that, let's say we will show you the real demonstration of what we are doing. Okay, so today we are going to make a kind of simulation of a planar transformer for a 2 kilowatt full refresh shift. And let's say the basic agenda for today is we are going to, as always, we have done the introduction and we are going to review our products, but not our products. I'm going to talk about more about the architecture of the product to solve a lot of technical questions that we are receiving lately, now that we are building more products. And we will end, let's say, with the demo and of the planner thing. So technology. So something that I realized that is going to be super interesting for the audience, according with the questions that we are getting, is explaining how is the architecture of our products. So let me show you here something. So this is a basic software architecture for the not computer science or software engineers. An API is basically a place where you connect a lot of blocks and you can use, let's say, you build applications calling APIs to get responses. So in our API that we have at Frenetic, we have a lot of things. And this is a small summary of things we have. But the good thing about this, let's say, the interesting part of these blocks that I'm showing here is all of them are kind of easily modified. You know what I mean? At the end is like we have, for example, modules for AI converter design. So we have here some modules that are using also AI engines, AI LLMs to help in the understanding or designing power converter. But also we have templates for power topologies. So we have topologies and we have templates, and even we have templates for the winding structures. But all the new winding structure can be added here if there is a customer need or something and can be connected to the API. Design algorithms. So if you want to design a converter or a transformer or a reactor, you need an algorithm that take decisions about how to choose the main parameters. And this is what is involved here in this block. Also, we have the models used for the losses, for example, or for the calculations, like analytical models or waveform calculations and all these kind of models. Then we have a new block that now we are going to see or show you today, that is the FEM block. This is a block that I will let at some point Jonas to talk a little bit more in detail. It's a block that allows us to run finite element analysis simulations. Using, in our case, we use Console on the cloud, and then we are able to run these simulations super fast. So this is the work of the team in Zurich, Richard and Jonas. And also we have modules just for download files. And this is actually the more silly modules in, let's say, in terms of complexity sometimes, but very, very super useful. For example, you can download LTS files. And this is like things that are connected to our API. And then on top of this is where we build products. So for example, we have our Frenetic AI, that is a tool for converter design and also planar design, but also we have our magnetic simulator that probably is the one that is more known in the industry. So these kind of products, they have different kind of application use cases, like okay, we are able to make the generation of waveform for customers, also suggest some design, and then run simulation for those magnetics. And what we are adding today to this portfolio is the Planar Simulation app. So basically, it's another product that is connected to the API, but from the upper side, from the products part, where we are able to design, let's say, sorry, to simulate planar magnetics. And you will see that we are getting use of the FEM models here. So it's super important in the planar simulation, this model, because you will see that is the main key. And today, in the demonstration I'm going to do, basically I'm going to start with a converter design in Frenetic AI. I will generate a design, I will generate some waveforms, and then I will use that information to run a simulation for a specific planar design that have been created here. So let's go. This is the demonstration we are going to do. These are the specs. So I'm going to take a 200 volts input, 270 volts output, and 2 kilowatt output for the full bridge phase shift with full wave rectification in the secondary. And now I'm going to share the other screen. So probably most of you are aware about this technology. So this is Frenetic AI, is the product that allows you to design a converter. So let's say that I'm going to just choose the full bridge phase shift, input voltage 200 volts, output voltage 270 volts, and the output power is 2 kilowatt. So I'm going to ask for the design the converters just for the sake of speed and because this is not the main task today. I already did this and I get here the responses. So I designed the converter, I have even a switching frequency, I have everything I needed, and I run also the design of a transformer. In this case, I run just the concentric case. So you can see this is the design of a full bridge phase shift using lead wire. Even though that the core could be like a planar case. And then I made a design for a planar. So the system generated a planar design with an ER64, and then I have here all the information for the design. So this is like 6 turns in primary, 12 turns in secondary, and number of layers, number of parallels, and I think that that's all. Also, we have here some core losses that are kind of relevant. So if I open this project, actually, I can also download the waveform, exactly the waveform that I will need in the case of for example, of the simulation. So I have also here just the transformer with the waveform with all the information from our tool. And even though also I have here all the information for the core window, all the information I will use later in the simulation of the planar. So as you can see in the first step, that actually, can you show your screen again? Because I have a slide that is going to be perfect for showing these steps. So we have 3 steps. And the first step, that is the converter and planar values extraction. For that, we need to extract the tune radio, magnetizing inductance, the waveforms. This is what we have, let's say I have just shown right now. And then now, let's say, talk about the planar design. Also, we have a core selection. We have a number of turns, thickness of each layer, turns per layer, number of parallels, and the position of the layer. And this is super important for the leakage, parasitic capacitance, and winding losses, right? So now that we have the 2 steps completed, we are going to jump to the third step that actually is showing you the new product. So, so now we have this application here. And in this application, what you can see is that, and this is the product of the planar, so I have several questions to answer. So I'm going to start with, we have to start writing the dimensions of the core. In the future, we will add, like if you choose the core, automatically will fulfill this information. But right now, it's something we have to include manually. So this is the dimensions of the core of the design for the 2 kilowatt case. Actually, for the core window. There is no gap in this case. And also for the leg dimensions, that is 25.4, and is round leg. So now I can move to the next step. So basically here is asking me how I want the PCB to locate it in the window. So 80% automatically of the width and the height. That's fine. So I'm not going to change anything there. And then now we're going to start with the configuration of the design. So we know that the design have more or less a 15 amperes of current RMS in the primary. I'm just using this just to have a reference of the current density here. And then the design has 6 turns and 1 layer per turn. So I have 6 layers. And the distance between turns can be decreased to 0.2 because actually we need quite more space here, but well, this is fine. And I'm going to increase the thickness of the layers to improve the current density. In this case, 14 amperes is fine. And now also the distance between layers, because you can see there is no space in the PCB. So I'm going to put 0.5. Now I'm going to the secondary, same thing. In this case is half of the current, 12 turns, 3 turns per layer. Here, 0.2 between turns, also to gain some space 0.2. Still, I get the current density is high, so I'm going to put again like the same thickness than in the other 3 ohms. I mean, here we have 20 amps, maybe kind of in the limit, but I think it's going to be fine. And now I'm going to add the waveform. So you can see now that we have the waveforms here. We can add as much harmonics as we want, but this will increase the simulation time. So I'm going to just use those ones. So now the system is going to run in the simulation. Just in case that everything fails, don't worry, I have run this before, so I have the other the results. But as you can see now, it's calculating the leakage inductance, capacitance, losses, even that I expect 0 losses in DC losses, but let's see. So this can take up to 1 minute. So this is a good moment for Jonas asking you about this console connection, let's say this connection with FEM. How does it work? Let's say, what is the benefits or what is allowing us to do now? Whoa,
Results are already here. Okay.
Hey, come on, it's working.
Yeah, I can explain a little bit the philosophy behind that. Like Frenetic usually always in the past used analytical models or empiric models like Steinmetz, or analytical models like for winding losses. We have analytical equations behind, and the advantage of that it's much faster. However, always limited to certain type of geometries, and we always were struggling a bit with difficult cases like planar, for instance, because you have so many degrees of flexibility, and especially you have air gaps. As an example in there, you have a magnetic field that leads to high proximity, or eddy currents in the traces leads to potentially high losses. And so we decided now for this particular case to choose a FEM approach, just because we think the accuracy here is necessary. Well, usually the clients are okay to wait a bit longer if the accuracy is given. So that's why we chose now a FEM approach, and we went then to search the right tool, and we decided to go with COMSOL. They have different reasons, but there are a lot of things considered that COMSOL is strong at. Like, for instance, if you have parallel windings, it also calculates the uneven distribution of the current in parallel windings. Actually, that was a question last week in the webinar, that whether we are considering this. In many cases we neglect this, but in this specific case here we do consider it, because it's thanks to FEM we have a much more option. So yeah, I think it's a new approach, and we will combine this also in Frenetic simulator. In the magnetic simulator, we will allow the user in the future to have more accurate calculations, maybe for the final designs using COMSOL. But that's the first tool that we developed in this way.
Yeah. And something, so now that we have the results here, you can see that for the moment we are showing winding losses here in the split in the windings, and also the leakage inductance in primary. Well, this is from primary to secondary, and the parasitic capacitance. But since we are running this simulation, I guess that at some point we can add more detail of the values. But I think for the moment, and for the sake of the first designs, I think that that's going to be super useful. And we're going to do something that if you will be using console by yourself or ANSYS, it will take you hours. But let's say, what happened if I want to do like a different combination of interleaving or let's say the other, whatever. So let's take a look. Here we have 6.7 paths. We have 0.4 microhenries. So what's happening if I going to take one layer, I'm going to move the layer, and I'm going to do like a zero interleaving. So I'm going to run the simulation with zero interleaving. Let's say what happened. So what I expect to happen is that leakage inductance increase, and also losses I expect to increase and maybe higher than can manage. What about the capacitance? Do we expect to increase?
No, we expect a decrease of capacitance. Usually, if the leakage inductance increases, then the other capacitance decreases because the distance between layers is different. So now I don't know if I remember the values. We'll see, but it probably will
was
be like
0.4 microhenries for the leakage and 6.2 watts of loss. Okay.
Yeah, so that was as expected there.
Okay, as almost double of the leakage and 1.8 more watts of losses here.
Yeah, I mean, it's super easy to change the layers, right?
Yeah,
If you would
can,
have
yes, choose the
your
layer.
console or ANSYS simulation,
Yes,
it's
you can here.
a bit difficult, and you can maybe also, if you want to have the leakage inductance integrated, play around with it, and you will manage to get to the value
fast. Okay, so since I want to left, we have only 4 minutes left, and I want to left some space for questions. I'm going to stop sharing, and then we can listen if there are any questions in the audience. The audience is actually even from Europe, from everywhere. So if there are any question, before jumping to the question, I think we have to say thank you and congratulations to Sheriff for working on this. Sheriff is one of our developers that he had been working in this product for the last 4 or 5 weeks. He has done a good job.
I mean, definitely thanks to Sheriff, but also thanks to Richard, who did the whole console model implementation. So,
and actually, the Richard is going to be the Richard work is going to be used also in the simulator. So, congrats, Richard. The other part here is, and I'm going to write my email in the chat. So if for any reason you are super interested in testing this tool soon, because basically the capacity, even though that you think that this is just FOMO, but the capacity of our servers for console and all this stuff are limited. So that's the reason we are now going to, even if we will have 1,000 potential customers tomorrow, we couldn't sell to all of them. So we are giving them priority to first Frenetic already customers, and second, to people that is attending these webinars are showing a first interest. So I'm going to write my personal email here. So any kind of request, let's say interest in really testing this for potential real use in your company, please send us an email, and I will, let's say, I will help you to try and also to get a meeting, let's say a proposal or whatever. So writing my email here in the chat. So let's go for the questions.
thank
you. Thank you, guys, for
sorry.
the great test. You have a lot of questions in the chat, but also in the Q&A tab. So,
and that's what I wanted to say. We have 2 places of question now. Let me try in the chat are a bit more questions. So let's start with these. Trace with units, I think millimeter, but it's not given. So if not, then we have to definitely add.
Millimeters.
Millimeter is given here as the, yeah. The prereq material has, of course, an impact on the capacitance. No, it's now standard. Maybe that's something good input. We might consider this. Then how accurate does simulations are? How does results compare to real testing? We are very confident that this is very accurate, especially because the the underlying models we do. Yeah, we will also do some testings. We did already some testings of certain model parts. We will also at some point release a fact sheet as we did in the past. So this is something we will do and share.
So there is also a question from Romy here that I think in the Q&A is interesting. That is about the losses per winding. Are they considering or covering proximity, eddy current, resistive losses?
Yeah, this is like all of them. Yeah, you have a FEM model, a simulation that calculates the exact current distribution due to proximity and skin effect. And yes, absolutely.
And yeah, the core losses are actually, you have seen in the previous calculation, are covered there. So you have the core losses in the system, yeah.
It's not in this tool yet, just because we decided to first tackle the more difficult part, that you would need to have a change in tool to get the core losses. But this is something, the integration of the tools is also a priority for us.
Maybe in the chat, well, the Spore Herbers to Altium. So this is in the first step here. You can see that that we are defining exactly how the layout it is. So one of the interesting steps that we have in the roadmap is to analyze what is more important for the users, and maybe exporting to Herbers to Altium or KiCad or whatever could be one of the options. But it's gonna depend on the users, because all of them will have, let's say, we will ask all of them, like, what is next more important for you? And we will include that, let's say, we will put that on top of our roadmap.
I think we also, we might not have time to answer all questions, but we have this LinkedIn private page. Maybe Elio can comment on that, and we can answer then the remaining questions there.
Yeah, somebody asked if the password for Frenetic Simulator can be used in the Planar simulation. So the password of your Frenetic Simulator, if I'm correct, will work on Frenetic AI, let's say in the that module, but not here, because this is something, it's an additional product. So if you're interested, if you're already customer, you will have priority. So just write that message to any of us or even to my email, and we'll try to give you access, let's say, or show you how this is going to be priced and everything. Well, it looks like a lot of people asking about the Herbers. So maybe this is growing in the, let's say, it's going up in the roadmap. This is like a summary.
We did already.
Losses. I think that we have answered most of the, let's say, everything is kind of similar.
Yeah.
And okay, for the sake of not making you waste, let's say, invest more time on this, we always try to be on track of half an hour. So we are already 3 minutes more. But Ellie, you wanted to, we have something else to share?
Yeah, I would like to share something before finishing this webinar. In the meantime, you can choose the last question you want to respond. Today, we have been talking a lot about Planar transformers, about the Frenetic new tool, and we would like to give everybody who has been attending this webinar with a special seminar for next Tuesday. I'm going to share the link, and I'm going to explain a little bit what is going next.
You are.
Okay, now, what I say, next Tuesday, 21st, we are going to be with us, the Professor Siwei Jan, talking about planar magnetics for power converters. He's from Technical University of Denmark, and I think it's very interesting because this seminar is going to be special because we'll have a limited capacity, and we are going to talk about some specific interesting topics. The seminar will take 1 hour and a half, and then we have opportunity to talk with the professor. So that's all from my side. It's important that I shared the link because you have the early registration opportunity because of the limited capacity for this special session. So be free to join now.
Okay, so thank you very much, everybody, and see you soon.
Yeah, thanks a lot.
Thanks a lot.
Bye-bye.